In Chapter 11, we're going to be focusing on things called sequences and series, and we're going to get in depth with two particular types, the arithmetic and the geometric. But in general, 11.1 just talks about sequences. A sequence is just a list of terms, and those terms are in a specific particular order based on the counter of the terms. So we use a sub n or a sub I to represent the nth term in a sequence. And this is term 1, 2, 3. So what you should see here is that n is the counter. You see n is 1, 2, 3, 4, and on. Okay, there are infinite sequences that go forever, and there are finite sequences where you're given the n that it ends at, okay? Now, each of these terms is actually a function of a variable n, where n is a positive integer. N usually starts at 1. For this section in this book, n is going to start at 1. When you get to calculus and you're using infinite series, which would be the sum of all these things, sometimes your counter will start at 0. Sometimes it starts at 2. You can adjust it as well, and you'll learn how to do that when you get to Calc 2. All right, let's look at this example where the nth term in a sequence is 3 times the counter minus 1. So the first 5 terms, when the counter is 1, you plug 1 in, you get 3 minus 1 is 2. Plug in a 2, you get 6 minus 1 is 5. Plug in the 3, you get 8. Notice that these are going up by 3 each time. That's because this is what we call an arithmetic sequence. Every time n changes by 1, your term is going to get another 3 added to it. That makes it arithmetic, okay? We'll talk about that in the next section. But you can see a pattern here, and notice that in this case I stopped at 5 terms. So this would be a sub 5. This is a4, a3, a2, a1, like that. Look at this one. This is what we call a geometric because the bottom is getting multiplied by the same number every time. It's also what we call alternating because think about what happens when n goes up by 1 and it's an exponent on a negative. Well, when n is 1, negative 1 to the first power is negative. Negative 1 to the second power is positive. Negative 1 to the third, odd powers are negative, even powers are positive. So you see how the sign is alternating here. That's what we call an alternating sequence. Notice also that the top is always plus or minus 1. The bottom is getting multiplied by 2. Every time that counter goes up by 1, you multiply by another 2. This is called geometric. A few more examples. If you're asked to find a particular term, you're just going to take that number and plug it in for the n. So 3 minus 5 times 4, 3 minus 20, the nth term, or the fourth term, sorry, is negative 17. For this problem, finding the third term, notice that it's geometric on the top and arithmetic on the bottom. That's okay. You're just going to plug the n's in. Oh, it's also alternating. Look at that. So a minus to the third power stays minus. 2 to the third is 8, and 3 times 3 on the bottom is 9. Okay, once you get comfortable with sequences, we're going to start doing something called series. And understanding series, especially infinite ones, can unlock a lot of doors later on in mathematics and engineering, in physics, and all kinds of sciences. So a series is just the sum of the terms of a sequence. This signal right here is a capital sigma, and you see that I have my counter starting at 1 and stopping at some value. This could also be infinity. and we've got whatever our function of n is in here. And when I plug in a 1 and I plug in a 2 and I plug in a 3, it's just the sequence, but we're adding all of the sums until we get to this top number. So example, if my a sub n is 2n plus 1, I'm starting at 1 and I'm going to 4. By the way, these n's become i's pretty soon. You can call your counter whatever you want, but most textbooks use I or n, sometimes j and k, but we'll talk about that in Calc 2 and Calc 3. Okay, so this is the situation. We're going to start with 1 and go to 4. So we plug in the 1, we get 3. Plug in a 2, we get 5. Plug in a 3, we get 7. Plug in the last number, the 4, and you get 9. And the sigma says sum them. So you add them all up and you get your answer. All right, some properties of series. Series are when you're adding the terms of the sequence. I sometimes say them backwards, so watch out. Series means it's a sum. If you have some constant multiplying your a sub n, you can factor out that constant. Think about it. This is the sum. Every single term has a factor of c. I can undistribute the c and just work with my series, find that sum, and then multiply the sum by the constant. If I have two things in here, two separate functions that are being added or subtracted, I can sum each series and then add or subtract at the end. Okay, something that you're going to see in this section, you'll also see it if you take probability. Factorials. The factorial notation is whatever number with an exclamation point. Some of your more advanced calculators will also have a key. Factorial means I'm going to take this number and multiply all of the numbers below that all the way down to 1. So 5 factorial would be 5 times all the numbers lower than 5, and you get your answer. Most of the time your factorials are divided. So, by the way, you can represent sines and cosines and things with infinite series notation, and they involve factorials. So they are alternating, they're factorials, and somewhat geometric. Okay, look at here. 10 factorial divided by 7 factorial. 10 factorial is 10 times all the numbers below it. That's a nasty number. But I'm dividing it by 7 factorial, so I'm dividing away all the numbers below 7. So what you should do in practice is take the biggest number and write out all the factors until you get to the other number and stop. This is 10 factorial because it's all the numbers from 10 down to 1, right? And then once you stop there, you can just cancel and multiply out the numbers on the top, and you get 5, 50, 40. No, you don't. Well, just look at me. I'm multiplied by the 7, but the 7 gets canceled along with everything else, and I end up with 72 times 10, 720. Sorry about that. Okay, one really cool thing is that 0 factorial is defined as 1. So there are cases where you will actually do this division kind of thing and end up with a 0 on the bottom, but 0 factorial is defined as 1. I have no idea why. Okay, here's some examples. Example 1, we're getting 4 terms starting at 1. Notice that my counter is now an I. We're starting at 1 and going to 4. This is an arithmetic because we're multiplying by 2 every time. So you plug in the 1, you get 5. Plug in a 2, you get 7, 3, and 4. And we're going to add these guys together. So when you add them, you get 32. For this one, it's alternating, and your counter is being raised to a power, which is interesting. Only 3 terms in this series. So negative 1 to the 1 is negative. 1 squared minus 1 is 0. So this is gone. Plug in a 2. That's a plus. That's 4 minus 1 is 3. Plug in a 3. That makes this minus. This is 9 minus 1 is 8. So I end up with 3 minus 8 is negative 5. Last one, here's an example where we have the factorial stuff. I talked about getting 0 in the denominator, 0 factorial. That's when you start with a counter of 0. And you use this particular item here when you're doing some stuff in probability with combinations and permutations and things like that. Also to find coefficients of binomials. I neglected to finish. I have the fifth term here, 5 factorial, 0 factorial. So this is plus 5 factorial on the top divided by 5 factorial. 0 factorial is just 1. So that's plus 1, and I end up with 31 as my answer.